You're watching a lithium-ion battery being assembled. It's a clean, quiet, almost sterile process. Robots place electrodes, roll separators, and seal the casing. This is the future being packaged. It feels like a solved problem, a matter of scaling up. But there's a hidden tremor in this assembly line, a geological fault line running directly beneath it. Because before this battery was a sleek, modern product, it was a rock. And not just any rock. It was a specific type of rock, dug from a specific type of place, processed through a specific and brutal industrial chain. The entire energy transition, the shift away from fossil fuels, is now hitting a wall. Not a wall of policy, or will, or investment. A wall of geology, chemistry, and time. This is the energy historian, uncovering the hidden systems that power civilization. We've been told a simple story. The age of oil is giving way to the age of electricity. Wind turbines and solar panels will generate the power, and giant banks of batteries will store it, smoothing out the sun and the wind, powering our cars, our homes, our world. The demand curve for these batteries is vertical. It's not just about electric vehicles anymore. It's about grid storage for renewable energy, backup for data centers, power for everything from tools to ships. The International Energy Agency projects global battery demand will increase tenfold by 2030. That's not growth. That's a cliff face we're trying to scale. And our climbing gear is made of minerals we've barely begun to mine. So let's follow the chain backward, from the finished battery on the shelf to the earth it came from. A modern lithium-ion battery is a kind of mineral sandwich. The cathode, the positive side, is where the real complexity lives. It's typically made of lithium, yes, but also nickel, cobalt, and manganese. The anode is mostly graphite. There's copper in the wires, aluminum in the casing. This isn't one material. It's a precise alloy of half the periodic table. And for the transition to work, we need staggering amounts of all of them. By 2040, the World Bank estimates we'll need 500% more lithium, graphite, and cobalt than we produce today. For nickel, it's over 100% more. This isn't a supply chain tweak. This is the industrialization of entire new continents of mining. And here's the first bottleneck: time. A new mine isn't a startup. You can't code it into existence. From discovery to first production routinely takes 10 to 15 years. You have to find the deposit, prove its size, navigate environmental reviews, secure permits, raise billions in capital, build the processing plants, and construct the infrastructure roads. Power, water often, in remote locations. The clock for 2030 started ticking around 2015. We're already behind. The transition now moves at the speed of digging holes in the ground. Now, let's look at the map. This is where the structural tension becomes geopolitical. These critical minerals are not evenly distributed. They are hyper-concentrated. Over 70% of the world's cobalt comes from the Democratic Republic of Congo, much of it from artisanal mines with profound human and ethical challenges. About 60% of the world's graphite refining happens in China. Indonesia and the Philippines dominate nickel production. China refines nearly 90% of the world's rare earth elements and over 60% of its lithium and cobalt. This isn't an accident. It's the result of a deliberate, decades-long industrial strategy. While the West focused on the digital and financial layers of the economy, China secured the physical, material foundation. They built the refineries. They own the processing technology. They control the midstream. So you have a demand explosion in one part of the world, and the means of production concentrated in another. This creates a dangerous dependency. It's the oil shocks of the 1970s, but with a more complex and brittle supply chain. One geopolitical tremor, one trade dispute, one internal policy shift in a key country, and the entire battery pipeline seizes up. The car factories in Germany, the grid projects in Texas, the data center builds in Virginia, they all share a single, invisible point of failure: a processing plant on the other side of the world. But the bottleneck isn't just about geography, it's about chemistry and economics. Not all lithium is created equal. There are two main sources: hard rock, mined in Australia, and brine, pumped from salt flats in South America's Lithium Triangle. The hard rock is faster to bring online, but energy-intensive to process. The brine is cheaper but takes years to evaporate in giant ponds. Each has its own environmental and logistical tangles. Then there's nickel. The high-grade nickel suitable for batteries is getting scarce. The industry is turning to laterite nickel ores, which are more abundant but require a monstrously energy-intensive process called high-pressure acid leaching to refine. This process is so dirty it often relies on coal power. So you have a paradox. To build the batteries for a clean energy future, we may need to burn more fossil fuels today. And this leads to the most brutal realization of all: the quality cliff. As we ramp up production to meet insane demand, we are forced to dig up lower and lower grade ores. This means more rock must be moved, more energy consumed, more waste produced for the same amount of battery metal. The environmental footprint of each new battery actually increases. The energy return on investment, the clean energy you get out, versus the dirty energy you put into mine and make the thing start to shrink. We are chasing a receding horizon. Think about the scale for a second. A single electric vehicle battery pack contains about 8 kilograms of lithium, 35 kilograms of nickel, 20 kilograms of manganese, and 14 kilograms of cobalt. Now multiply that by the goal of 40 million EVs sold per year by 2030. That's 320,000 tons of lithium. That's more than 5 times the entire world's production in 2022. The numbers are so large they feel abstract, but they translate into mountains of waste, oceans of chemical effluent, and a staggering draw on global electricity and water supplies. The green future has a hidden, massive footprint in the present. This is the core contradiction of the transition. We are trying to replace a fossil fuel system, which is incredibly energy-dense and logistically refined, after a century of work, with a mineral-based system that is materially intensive and geographically fractured. Oil flows through pipes and ships. You can redirect it. You can store it in tanks for years. Battery minerals are solid. They must be dug, crushed, chemically separated, shipped as powder, manufactured into components, and assembled. The supply chain has 100 critical choke points, each one a potential stall. And the market is already signaling the strain. Lithium prices skyrocketed by over 500% in 2022, before crashing in 2023, when demand forecasts were slightly tempered. That volatility isn't a bug. It's a feature of a system trying to find a new equilibrium under insane pressure. It makes planning impossible. No automaker will commit billions to a gigafactory if they can't be sure of the raw material price or supply next year. The entire financial model of the transition assumes steadily falling battery costs. But if mineral prices are on a roller coaster, that model breaks. So what's the way out? The solutions are as hard as the problem. First, mining in new places. The West is scrambling to develop mines in places like Canada, Australia, and the United States. But this runs into the 10-year timeline problem and fierce local opposition. Nobody wants a mine in their backyard, even for a green cause. Second, recycling. It's essential, but it's a future solution, not a present one. There simply aren't enough old EV batteries to recycle yet to make a dent in primary demand. The battery wave is still building. It hasn't crashed ashore to be collected. Third, new chemistry. Sodium-ion batteries, lithium iron phosphate batteries that use no cobalt or nickel. These are promising, but they often trade off some energy density or performance. They help diversify the pressure, but they don't eliminate the mineral demand. The real, uncomfortable truth is this: we have backed ourselves into a corner where speed is everything, but the systems that enable speed are slow, dirty, and concentrated. The battery is the heart of the new energy system, but that heart is made of materials that are scarce, difficult, and politically fraught to obtain. We are trying to perform open-heart surgery on the global economy, while the patient is running a marathon. The transition is no longer a question of will. It's a question of logistics. It's a question of digging, refining, and shipping at a pace never before seen in human history. And it's a race against the very real limits of geology and industrial capacity. The sleek, silent future of electric transport and renewable grids depends entirely on the oldest, noisiest, and most disruptive industry we have, mining. The bottleneck isn't our ambition, it's the earth itself, and the clock is ticking. If this gave you a new perspective on the material foundations of our future, hit subscribe. Let me know in the comments. Do you think the mineral bottleneck will slow the transition or force a breakthrough we can't yet see?